Hello everyone. So in the continuation of CTQ 11, whatever we have seen till the part 2, we have seen the gain calculation in two different ways. Direct calculation in the negative feedback configuration, and after that first consider the open loop configuration, then calculate the open loop gain. After that, using the negative feedback concept, just write the closed loop gain concept here. Now the one more extra concept that I will discuss here is nothing but the loop gain concept, that we'll see the loop gain, and after that we'll use some transistor level model for this amplifier block. Okay, so this is important block, amplifier block, that we can realize using some transistors level structure, that we can use maybe 5 transistor OTA structure or anything else we can use for it. Okay, so let first calculate the loop gain. And what is the significance of loop gain, we will discuss shortly. Okay, so how to calculate the loop gain? For that, the step is that first break the at some high impedance node. The concept of breaking the high impedance I'm not telling here, but I will tell in some other video. Okay, the second thing is that consider input, which is actual input, that is your V in, to be shorted, because we have different input excitation, and provide an excitation at the input of broken. Okay, what is the input of broken loop? I mean to say, if I break this loop here, because it is a high impedance node, we can see there is a high impedance for the input of the amplifier. So if I break my loop here, what I can consider, this voltage I can consider the feedback voltage, and this consider I can read a source that I am applying the excitation externally. And in that case, I will consider this node to be 0. Okay, so what is the structure we will see here? The structure we will see A plus this node to be ground, and here I am applying some excitation short or V source, and here I am observing my V feedback. So what is that? R is my feedback. Okay, it's shorted. So what is this voltage? Now we are in the open loop configuration. We can simply write Vx is, this is negative, minus A times Vs, and then what is this? Vf. Vf is nothing but V out is equal to what? Simple, I times ID times R. And what is the ID? We can see from here, because we are in the open loop configuration. So the ID can be written as ID is GM VGS for the transistor, which is nothing but GM VG is your gate voltage, and S is your output voltage, which is another V out is also Vref. GM, sorry, not Vref, it is V. Okay, so what I can write here, Vf is GMR Vx minus Vf. This is the Vf we are getting here. Okay, and Vx we know, these are two equations. This is the one equation, this is the second equation, and we can solve these equations, and we can write the transfer function in terms of Vs by Vf. Okay, sorry, Vf by Vs, because now we have the different excitation, that is nothing but Vs is my input excitation for loop gain calculation, input excitation for the loop gain calculation. Okay, and V feedback is the feedback. Our target is to calculate V feedback by Vs. This is my minus of loop gain, it will come. Okay, so what we have seen, Vx is nothing but minus A times Vs was the one equation, and second equation is what? Vf is equal to GMR times Vx minus, so it can be written as GMR times Vx is nothing but minus AVs minus Vf. So Vf can be taken common here, Here minus is also there. 1 plus a GMR equal to minus a GMR VS. So what you will get, VF by VS is equal to minus a GMR divided by 1 plus a GMR. Okay, so this is the loop gain. Negative sign is just for this inversion of sign. Okay, that's why usually when we plot the Bode plot for the loop gain, the phase comes different that of the open loop system or closed loop system. Okay, so what loop gain we got? Loop gain, a DC loop gain I should say. DC loop gain, I got AGMR divided by 1 plus GMR A. What is the definition of loop gain? Actually, the loop gain definition is nothing but it is beta times open loop gain in terms of DC. And in the frequency domain, we write the loop gain equal to beta times a loop gain in the frequency domain. Okay, so what we can see as beta equal to 1, so our loop gain is coming as equal to the open loop gain, which is nothing but AGMR by 1 plus AGMR. Okay, this is my loop gain that I am getting. Okay, so the closed loop expression, closed loop gain CL can also be written as, and I also like the first in the means S domain. It can be written as what? AOLS divided by 1 plus beta AOLS. We usually write it like this. So if I what I do, if I multiply with the beta and divide by beta, then what I can write? It can be written as beta AOLS divided by 1 plus beta AOLS times beta. So what I can write, the closed loop transfer function in the frequency domain can be written 1 by beta loop gain in the frequency domain divided by 1 plus loop gain. Okay, so DC value of the loop gain is nothing but AOL of 0. Okay, so I'm not concerned about that. What I will get, DC closed loop gain is nothing but 1 upon beta DC loop gain divided by 1 plus DC loop gain. Okay, so what we ideally want, we want the loop gain should be much greater than 1, so that ACL, the DC gain, is comes nearly 1 upon beta. This is the closed loop DC gain. Okay, so with this assumption, what happens when we consider the loop gain to be much greater than 1, our closed loop DC gain comes 1 upon beta. And what happens when a closed loop gain is 1 upon beta, or this is nearly very large? Ideally, I will say it is nothing but beta times AOL. If this thing is much greater than 1, ideally what we can say, if my AOL of 0 is much greater than 1, or I should say 1 upon beta, then what we can say, our error is minimum. Error is minimum. What is the error that we have seen? This thing I have discussed in some other video as well. This voltage called the error voltage. Ideally, it should be as minimum as possible for the better system. If this is my AOL, this is the beta. Okay, this is my beta voltage. So beta is coming out to be 1 here. So if my AOL, let's say, is infinite or very large, then what is their error voltage? Error voltage nothing but V in minus V out. And what is the V out? V out is nothing but AOL times V error. So what error should come? V in minus AOL V error. So from here what we can write, V error or V difference voltage is nothing but plus AOL by V in. So what relative error comes? the error with respect to input comes as 1 upon 1 plus AOL. If AOL is infinite, this relative error comes to be 0. What does it mean to say my input voltage equal to the feedback voltage for the unity feedback system, or my input voltage equal to beta times the output voltage? If my beta equal to 1, I would say my output voltage equal to input voltage. It is the perfect tracking of the input. Okay, for the unity feedback system, I will say my output exactly equal to the input voltage. So there are many more discussions related to this concept depending on the complete analysis of the negative feedback system. I think I have discussed this thing a lot in 5T OTA frequency response. You can visit this playlist also, frequency response. So 5 transistor OTA structures frequency response has taken 8 to 10 videos. Okay, so one can go through these videos, the complete sequence of frequency response is there, and you will see all these concepts where this loop gain matters and how to analyze the circuit in terms of means Bode plot and everything. Okay, so this was a thing that I had to made. Now I want one more modification, that I want to realize my gain block with some structure. Just to make you aware of one thing, what is the structure? My structure is this: A plus minus. This is my input, and here I am taking the feedback. Okay, so what can we do? We can realize this circuit, realize this structure A with some transistor level design, and I'm using a 5 transistor OTA structure for this. Okay, if I'm using the 5 transistor OTA structure, I can have the different realization of this A. How to realize this A? This A can be realized in the way like this is the inputs, this is the output. Okay, this is the input, this is the output. I can realize it like this: GM cell is taking the input voltage, generating the current, and this current, the source current something, is fed into this capacitor voltage, and I'm getting the output. So this is the one way of realizing the A. This entire thing is your A. How it is coming out, that we can see what my IS is, current coming out is nothing but GM V in, and how it is charging my output voltage, oh sorry, capacitor. Then what you can see, P out is nothing but this I times, what I will say, 1 upon CLS. So GM by CLS times V in. What is the gain? V out by V in is nothing but GM by CLS. But when it comes, we have seen this thing already in the 5 times 2T series. When I'm considering my GM cell is ideal, mean to say the R out of the GM cell is infinite, then only we can say the infinite gain response come into the picture. Okay, it's an infinite gain, and omega 3 dB comes to the 0, and what omega UGB comes, omega UGB comes GM by CL. So this is the structure for practical GM, sorry, ideal GM cell. But when we have the practical GM cell, means I have some finite output impedance also, and what exactly we can say, this gain term can be reduced to V out by V in of S can be reduced to GM by what I should say. Okay, what is the current? Current is a GM by, sorry, my current is GM V in. This is my current, and when this current is charging, okay, then what we have two things. This current is charging. Yes, this current times I can say G out plus 1 upon CLS. Okay, what mean to say? G out is nothing but 1 upon R out. So this is the practical. What we'll say, yes, it's fine. So from here, what we can say, you can write expression for this GM in the way, CLS G out, and GM in current Y G out. You can have the voltage. Okay, so I should, instead of writing B in here, because I already have taken the transfer function, GM times expression. Okay, so when we have finite impedance, then we have to consider this also. So this is your A. This is your A. Okay. So in terms of DC gain, what you can say, DC gain here comes out to be at S equal to 0. So this term is going to be, I think the expression is not looking correctly here. GM IR na R out plus 1 upon CL. Okay, one mistake I am doing here. Mistake we are doing here is, okay, so this expression is not correctly written. So rather writing this, I write it like this. Okay, so it would divide by G out plus CLS. Okay, so what is exactly gain is GM by G out plus CLS, and what the DC gain comes? DC gain comes GM by G out, which is equal to GM by, sorry, GMR out is the gain. So this is the practical gain block we can implement like this. So what is the ideal GM cell? When there is an ideal GM cell, our gain is infinite. So in this case, what is the DC gain? This is nothing but infinite. What is the DC gain in this case? It is a practical value, which is nothing but GM R out. And R out, we know, if we have this structure, we can find the R out. So if I am using this gain block by, sorry, by using some sort of GM cell, we can analyze in this way. Okay. So this is our amplifier block, and it can be implemented by using the GM cell, and its current when is fed to some load, which load is nothing here, the parasitic in this case, no external load is applied, so parasitic cap is here, and from here what we have, the DC gain here is nothing but GM R out. What is the R out? R out is the impedance looking at the output for this cell. So this is my complete. A of 0 is nothing but this A, which is nothing but equal to coming GMR out in this structure. So this particular thing, the GM cell, practically I can implement using 5 transistor OTS structure. Okay, so this is our GM cell. Okay, so this GM cell is a simple 5 transistor OTS structure. The point here to tell you how we can see for this gain block. Okay, so this is the input what we are applying here. This is the input what we are applying here. So simply this is nothing but a GM cell, and this GM cell can be treated as a gain block. Okay, so this is the extra thing that I want to tell about this question. And if something is remained for this to analyze is, what I can say, when we are having power supply perturbation. Okay, noise disturbance in power supply, the power supply is fluctuating, and what will happen for this structure? So this is my gain block. Power supply of this I am considering to be constant, but I am considering that this power supply, especially what I am driving here is a VDD or VDD, is having some disturbance or some perturbation. Okay, so here I am having some perturbation in this power supply. I am considering the power supply of amplifier block is regulated, and I am not worried about that. Here I am having some perturbation that I call del V. So I have to observe and what is the effect of this at output, and without this what is the effect on this output. If I am using only this structure, and is there any perturbation in this VDD, that is this del V, and what is the effect of this perturbation on the output voltage in both the circuits, we have to compare. So this thing we will see in the next video. Okay, so for this what we have seen, We have seen two things here. Then what is the concept of loop gain, and how it can be relate with the what do you say? How it can be relate with your closed loop gain and open loop gain. Okay, so relation of three things here: loop gain, closed loop gain, and इससे ऊपर open loop gain. Okay, so these three things are very important from the stability viewpoint. And after that, we have seen that how we can realize your A block. So this thing is GM cell, the concept of GM cell, and after that, how we can realize this GM cell just by using the 5 trans 2T structure. Okay, so rest all the detail of this particular discussion about the GM cell and 5 trans 2T structure, frequency response. You can just follow the 5 trans 2T series. Okay, so this is enough for this video. Thank you.